It's Andreas Aardal Hanssen, who will do a talk about threading. Yeah, welcome, Andreas.
So, welcome to the threading talk. Hope my voice isn't too loud. Okay. My name is Andreas Hanssen, and this is a talk about threaded programming. Whenever there's a talk with an audience this big, there's always the problem of trying to find something good to give to everyone. And I suppose everyone here has a different expectation for this presentation. So it's very important, the thing that Hanna mentioned about the evaluation form, that if you find stuff that you like or you don't like, then just throw it down, because we're going to read through every single one and use it to improve next year's conference. So, and with so many people, I'm going to have to limit our communication pipeline to like 1 bit, so hand up and down. After the presentation, I'm going to do a little Q&A thing so you can ask questions, but if you have real difficult questions, we'll have to take it after the talk. Let's see here now. So, who am I? I am Andreas Hanssen. I have been part of, before working at Trolltech, I was part of the Scandinavian demo scene. I don't know if anyone knows what the Scandinavian demo scene is. One guy, good. I was part of a demo group called the INF. And I've also done some open source development. So I'm the author of the Blink IMAP server. And at Trolltech, I do I/O and plugins, threads, image formats, basically stuff that happens behind the scenes. And I think one of the most important aspects of my job is trying to remove mud. And when I say mud, I mean whatever comes between what you want to do and what is absolutely necessary for it to happen. So I'm working a lot with optimizations, and very often when you do optimizations, you come to this point where you find out that no matter how much you're doing, you still got this little delay that it has to take a second or two. And because of this, I'm also working with the threading module of Qt. So, I also, besides everything else, I've also done some imaging, and I wrote Plastique Style together with a colleague of mine. But that's, of course, not relevant for this talk. About concurrency and threading. Let's see here now, if I can get this stuff to work. We're going to talk about multi-threaded hardware and multi-threaded applications and the difference between the two. Also talk about how to make your code more threadable. Then I'll talk about threads in Qt, and both the threads we use inside Qt and also what thread support we expose through the APIs. I'm going to talk about some of the cross-platform considerations. Now, Qt is, of course, cross-platform, but threads are conceptually not. There is so big difference in how threads work between platforms, but I'm going to get back to that afterwards. A very important part of this talk is connected to the handouts that you've got. I'd like to demonstrate a couple of threading patterns, threading design patterns or models, if you may, that hopefully will make your threading life easier. And at the end, of course, I'm going to talk about what happens when disaster strikes. Because one thing, of course, is that if you're doing threaded development, you really have to have a passion for making application crash. And threaded applications crash spectacularly. And at Trolltech, people bug me for being the guy who bounces off the walls in joy. If I found yet another way of crashing an application beyond control, so that there's no way of finding out what went wrong, that's my day. And what was I to say? Hippopotamus. Yeah. So here comes the first slide. Let's see now. Dual CPUs are real cool. I'm an early adopter. I'm one of these guys who always goes out and buys the most modern hardware that you can get at about 4-year intervals or something like that. So I've got a dual CPU machine at home. Dual CPUs, anyone? Not too many, okay. So dual CPUs are mostly considered old school now. One of the reasons being that there's a physical distance between the two CPUs they're sharing their memory, and that, they're sharing one memory management unit. If the two CPUs are trying to talk to this unit, then they have to travel. The signals have to travel a certain distance. That introduces latency, and of course with a dual CPU system, there's no way getting around that. In some cases you can get 50% of your bandwidth only. One of the core models, one of the core problems of dual CPUs, of course, is memory. It's heat and space. If you do an X-ray of my machine at home, I'm sure you can find like a hairdryer inside. I've got these Thermaltake Volcano fans on top of each of my CPUs. I'm trying to cool those bastards down, but okay, so Intel has got hyperthreading. That's pretty common today. Hyperthreading model is basically a single CPU. It's a single CPU. There's no parallel execution other than a couple of operations that can be done at the same time as, for example, you're waiting for memory. But we're seeing much more today that there's going to be a move against multi-core, dual-core CPU technologies and other technologies. But my biggest message here is that today we're still mostly in single CPU mode or hyperthreaded mode. So the aspect of threading that goes to getting more performance out of your application is not as important as concurrency. So what's a multi-threaded application? Basically, you've got one process, always one process. There's one main thread. In Qt, that's the GUI thread. And you have one or more separate extra worker threads that you can use like you want. There's a shared heap, of course, between all these threads, but there's separate stacks. And this is radically different from single-threaded programming, where you've got virtually a limitless stack size. When you're doing thread programming, you have to limit the stack size. So if you've got 100 threads, each of these guys has to have a stack. You have to reserve space for that stack. This is usually done by the operating system, but every operating system does this differently, and you might get surprised. So also, yeah, latency is the enemy. Performance is a good thing. It's a bonus that you get if people have these advanced dual CPU, multi-core machines, but basically concurrency is what we're looking for. If you have this image that you need to load, and it's a big image, can't get around it, it's going to take 3 seconds to load, then at least you should make your GUI responsive by putting this thing in a thread. You're not making it any faster, maybe, but you can make that progress bar or whatever spin. You can maybe allow the user to do several things at the same time as you're loading that image, so the impact doesn't get so big. And as an example here, in 4.1 you'll see that we've included a BitTorrent client. And the purpose of this client is to give you a feel of what a complete application using both networking and threads at the same time looks like. Got it to work. That was the wrong slide. So the BitTorrent program, just for a simple overview, operates mainly in the GUI thread. Networking code is very little affected by threads in general. What you can do is you can, if you have several connections, like 100 connections, and your network protocols are very round trip sensitive, then you can get like lower round trip times if the event loops waiting for network operations are not depending on the GUI. But in this example here, they're actually running in the same context. What we've separated out in the BitTorrent client is file operations. Just to take a little summary of the BitTorrent protocol, the idea is that you have one typically very huge file you want to download from the internet, and you connect to maybe 50 different peers on the network and download segments of the files. And those segments can be as little as 16K, and they're typically spread out through the whole file system. So you can download the first chunk and the last chunk at the same time. If you're doing this with 50 connections concurrently, then of course your hard disk is going to go seek between all these different places. Got to read this, got to write this, got to read this, and the I/O implications of a BitTorrent client are immense. So if you see any of these clients out there and then go check the load of your machine while you're downloading a big file at a high rate, you'd see that the program is using 30, maybe 50% CPU, and the load on your disk is pretty serious. This program here uses about 3% to 10% CPU, mainly because, I mean the GUI part of it, mainly because all file operations are done in a separate thread. Whenever we receive a packet from the network, we send it off to a file manager thread. The file manager thread has the option of gathering up all these operations, maybe ordering them sequentially, writing them in one go. So it seriously improves the performance of your application. And not to mention the responsiveness of the GUI. In this program here, there's no latency if you click all the buttons and all this, but because it's not affected by file operations. So, threadable code. It's very important when you're writing multi-threaded programs that you think about threading from the first point when you're doing the design of your objects. The approach that we often choose is to have these objects live completely inside a thread. That means that you have a completely isolated responsibility area which is handled in a different thread. Minimize the communication that you need between the threads, because the very moment that you need to communicate, there's very, very often a lock somewhere. And the lock means that there's a single point where these threads are going to meet up and exchange data. That's not concurrency. That's basically a real performance impact on your multi-threaded application. You want to minimize that. So how do you write reentrant? I mean, how do you write threadable code? One thing is that you want to write reentrant functions. And reentrancy and thread safety is a term that comes up over and over again where people confuse these two. Typically in Qt we say that we don't support thread safety in this function. This object isn't thread safe, but it's reentrant. What that basically means is that, for example, for the QObject case, you can have a QObject in one thread. You can have a QObject in another thread, and the two will not mess up each other. That's reentrancy. There's no shared data between the two necessarily. That's reentrancy. And that means that the two can operate on either side, and you know, they will basically just run at optimal speed. They won't mess up for each other. You don't have any locks between them. Thread safety is more like you have a queue list with lots of data, and you've got two threads who want to write to that list at the same time. So what we can do is we can make QList thread safe. If we do that, then every single operation you do involves a lock. And that means that you destroy performance for the common case, at the benefit for the rare case where you need to write to the same list at two threads at the same time. Rather, if you write QList as a reentrant class, that means that you can have one list in one thread, one list in the other thread, writing to them simultaneously with full concurrency. And this is where the whole aspect of designing threadable code comes in. You often end up thinking, I would like to do something which involves writing to the same list. And if you do, then very often it can be smart to think, is there some other way that I can do this, where I don't have to write to the same list? So there's this little story from when I was a kid. I grew up in the US, and I did two things when I was a little kid. One of them was programming in GW Basic on my dad's computer, and the other one was playing soccer. And I was never really a soccer guy. I've never been a sports guy, because basically all sports are fundamentally unfair. So what's unfair about sports? Well, first of all, it's not always your fault, even though you've got the ball. You can mess up, but it's not necessarily your fault. So there's this little particular scene that I remember from running up towards the goal, and then I was 6 years old, by the way, so I had this one other guy at the team who was, all the girls, you know, liked him and everything, and they were running, he was running with this ball, and approaching the goal, and of course the defense comes to take the ball away from him, and I shout to him, pass the ball to me. And so what does he do? He kicks the ball into my feet. So I stumble, step on it, stumble on it, fall onto my nose, nosebleed, big embarrassment, and everyone was wondering, what was that all about? This is, of course, related. This is not necessarily a digression. It seems to be. So somebody kicks a ball into your feet, you fall over. This is multi-threaded programming, basically. My dad realized that I had to become an engineer. So concurrency is king. Try to avoid a lock whenever you can. Avoid the lock. You know, QMutex solves everything. Put the QMutex in, wrap it around, pass it on, create it on the heap, and lock it and unlock it and everything. I've seen people, even at Trolltech, we have had projects where we're doing multi-threading, and what people do is that in the beginning of their loop running in a separate thread, they grab a lock. Then they do a real complex operation, and then at the end of the loop, you free the lock. Beginning of the loop, you take the lock again. So in practice, the lock is always held. And then on the other side, there's another thread who does the same thing. And so these two threads can never operate concurrently because they're sharing a lock. This is not multi-threading. You want to avoid the locks whenever you can. The other thing is that you want to lock data. The concept of locking code is very old. It's very easy to create a mind map of the whole idea of locking code. Excuse me. So locking code is basically about, at the beginning of a function, I acquire a lock. At the end of the function, I'll free it. So whenever anyone wants to call this function, they're acquiring that lock, which means there's no reentrancy in that function. There is no concurrency in that function. But suppose that that function is just used to modify elements in a list. Now, maybe you can access the different elements in the list concurrently. I mean, not the list itself, but the elements in the list. And if they're consistently always accessing different parts of the list, maybe you can just drop the lock. Because, I mean, they're not stepping onto each other's feet. No lock, there you have the concurrency. And then there's, of course, the third point, free up the lock as soon as possible. Like with the function that locks at the beginning of the loop and frees at the end of the loop. You know, you want to lock only to access the particular data you need for that operation and then free the lock immediately. You don't want to do that complex operation while holding the lock. First example here, just to illustrate it all. Second here, at the bottom here, shows that you're actually creating one mutex for every element in the list, and then you can acquire a mutex for that element in the list. This is if you want to read and write, maybe write to the same element at the same time. If you're just reading, you don't need a lock. If you're writing from two threads at the same time, you can get away with locking data instead of locking code. The top one is an example of locking code. So I've got some threading models that I'm going to walk through. I'd like to stress the importance of a threading model. Whenever you want to use a thread, it's very common that you want to do something similar to what people have tried to do before. In essence, there's like a limited number of ways to use threads efficiently. Of course, you've got exotic ways of using it. I'm going to go through that at the end. There's an upside-down parser thread model that I'm going to show. Then there's the single-shot task thread. That's a thread which is very commonly implemented where you create a thread because you just need to do that SQL query, but you don't want the GUI to hang up. So you create a thread, insert this little statement that says select from in, join, and like whatever. And you end up with a very complex operation. Just do it in the thread. That's what I call the single-shot task thread. Bad thing is there's the overhead of forking and creating that thread. On some platforms, that is a significant overhead. And the thread just dies right afterwards, so we even have to clean it up. So at some point, you're going to have to wait for that thread to finish. This is a very single-shot task thread is very compatible with platforms where you don't have multi-threading. Because if you don't have multi-threading, you could get away with just doing that operation immediately. If you have code where there's a dependency that somehow prevents you from doing that thing immediately, then I would argue that you could try to reconsider how you've designed your threading model. But the first one we're going to go through is the one called the lazy worker thread. The lazy worker thread is my favorite model. It involves creating a thread immediately, not when you need it, but creating it immediately. And then the thread immediately goes to sleep. Because waking up a sleeping thread is fast. Creating a new thread isn't slow, but it's significantly slower than waking up a sleeping thread. The sleeping worker thread is basically a thread falls asleep immediately. Whenever something's ready to do, whenever there's some job, some data that came in that needs processing or whatever, the thread wakes up, does whatever it has to do, and then it goes back and checks, is there anything else I need to do? And if not, it just goes to sleep again. If there is, it'll just continue working. This is what we're doing in the Mandelbrot example. You've probably seen the Mandelbrot example. It's in examples, threading / Mandelbrot, or something like that. And the idea there is that generating a Mandelbrot fractal can be time consuming. And we've inserted an algorithm there which is particularly slow. It's intentional. It's supposed to be slow because the idea is that you have a GUI where you can zoom in and zoom out of a Mandelbrot, move around and all these things. And the GUI is responsive. So it always allows you to zoom in. Whenever you roll the mouse wheel or click the plus or minus buttons, you always get immediate feedback. But the actual rendering of the fractal happens in a different thread. That thread is sleeping, but once you give it new coordinates, it'll wake up, render a new fractal, and then it'll send these results through a signal. So I'll show later. So in the handouts, I know I've got some handouts that most people have got. I don't know if somebody didn't get those handouts, then that's because we basically might have ran out of them. There's some here, is it? Lying here in the front? None left. That's not handouts. But we're going to put this stuff up on the web so you can get it after the conference if you didn't get the handout right now. But I'm going to just go through 3 of the functions in the handout. Ooh, interesting. So there's a public function called loadImage in this thread. The example that I'm going through is an image loader. And the idea of the loader is that you can just tell it, please load this image for me. It'll do it in the thread, and then it'll emit a signal when it's done. And the signal argument contains the QImage result of reading the image. So this is a slightly academic example, as we love to make these little academic examples that might not apply directly to your logics in your business logics, but it shouldn't be too hard to find a map between the two. It starts off by grabbing something we called, grabbing a mutex called the QMutex locker. And QMutex locker is basically just a function that acquires a lock. You pass a reference to the address of a mutex. And once it falls out of scope, then it'll free the lock. And then after grabbing this lock, it checks if our list called files to load is empty. If it's empty, then there is a chance that the worker thread, the sleeping worker thread, is sleeping. So we'll call wake up. Cond is a condition variable, QWait condition. I'll go through that in just a second. So after waking up this wait condition, waking up the sleeper, we're still in the calling thread. So we append the file name that we want to load onto a shared list, and then we return, freeing up the lock, and then the worker thread can continue. This here is a very, very important aspect of threaded programming in Qt. We basically start our destructor by waking up everyone who's waiting on a wait condition. And then we call the function QThreadWait. QThreadWait is similar to join in other terminology. The quit variable here is set to true, signaling to the worker thread that it can quit. And you'll see from the run function, ooh, here we go, that the run function is basically a loop that loops forever. Now forever is, as most of you probably know, a keyword for just while one, or for nothing. So this is the worker thread's implementation. This is the sleeping worker thread's essence. What it starts by doing is grabbing a lock. And then it checks if its files to load list is empty. And if it's empty, then it goes to sleep by calling condition.wait. This will make this thread fall asleep and then freeing up resources and everything like that. The only guy who can make this thread return from this wait here is the function called load file, which goes condition.wake1, or the destructor which calls wake all. If the destructor calls wake all, then it will also set the quit variable to true, which will mean that from this loop that we've got here, you'll see that the thread will exit immediately. Otherwise, it will grab one single file name from the shared list of file names and then immediately free up the lock. So now the other thread who is appending file names to this shared list is free to do whatever it wants again. I mean, it can append new lists again, new files to the list. And it finally ends up with emitting the signal image loaded, which is a new feature of Qt4, which I think is pretty neat. You can emit a signal from within a thread, passing QImage result of what file was loaded, including the file name for reference. And Qt will handle that for you. It'll be emitted asynchronously in a queued fashion. After it's emitted the signal, it'll go back to locking the mutex that protects our shared list again, and then check if there's more images to read. And this means that if you have one loop in your main thread saying, load these 1,000 images to me, then this worker thread will not go to sleep until all those have been loaded. But in your GUI program, you can just go put this image into that place, put this image into this icon, put this image into, whatever, asynchronously. And that's multi-threaded programming. So the single-shot task thread is, there's many variations around this thing, but typically it gets its job description from its constructor. So you pass, for example, the file name to its constructor, and then you call start on the thread. Start function in QThread will start the thread eventually in the background. And then the thread will do whatever it's done, and then at the end, the thread will typically emit a signal just to say that, okay, I'm done. And the task that it's supposed to do is not done in a loop or anything like that, like with the former example, but it's done immediately. So in the handout, you'll see that the data writer example here, this example is a class that's responsible for writing a huge byte array to disk. So you've got a 10 megabyte byte array that you want to write to disk, and you know that it's going to take a while, and it's going to lock up the GUI while you're writing that file. So you just put it in a single-shot task thread, go start. And when the file has been written successfully, it'll exit. So you'll see from the run function that the only thing this thread does is to write that file and then emit done. And this here is a rather exotic model. This is one of my favorites. You know that when you want to write a parser and you have no control over when data will arrive, there's two things you can do. The one thing is to wait until you are positive that no more data is going to arrive. So for example, you're reading off the network, and you know the network might give you your 10 megabyte XML file or whatever, incrementally, blah, 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 blah. You don't know how long it's going to take until it's done. And the simple approach to that problem would be that you just block until you get the end tag or something like that, and then you're like, oh, I got it all. So you store this whole thing into memory, and then you say, parse it. Well, a better approach is to parse it incrementally. And the problem is that writing a parser that works on incremental input is really hard. The only parser that we all know how to write, really, I mean, we all know how to write, is the recursive descent parser. Recursive descent parsers, working on one single file, one array, it's easy. You just go read some stuff, You know, if I don't have enough data left, it's a failure, and I'll just return or throw an exception or something like that. But if you, if things are asynchronous, if you don't know how much data you're going to get, then you have to have some way of feeding data into your parser, and then the parser itself has to have a consuming step where it's supposed to consume more. Like in the QXML simple reader, or is it in QXML input source, you can feed the thing by saying parse continue, please continue parsing. And although our XML module is not the fastest in the world, it has an implementation which is very flexible. It allows you to read XML files incrementally. And this implementation is done by a table parser. Table parsers are really difficult to write, and it's very hard to maintain, very hard to find bugs in them. There's basically just a couple of huge tables, and then there's code that just jumps and increments pointers and checks, you know, stores state into a stack, and it's all real complicated. While the recursive descent parser, you just want to go, okay, parse this, and then inside the parse this function, you go parse that. If that didn't work, return. But if the input is incremental, it's real tricky, because then you have to go, if I at this third character in what I think is a string don't have any more data, then I either have to block or I have to, you know, somehow store all that state. It's real hard, real complicated. So the upside down parser thread. Basically, you implement your recursive descent parser inside the run function of a thread. And it grabs its data from a shared string. And in the get car implementation that you can see in the handout, this thread will block when it's out of data, and you don't have to think about that when you're writing the parser. The parser can just go read whatever, you know, get some data and everything, and the moment you run out of data, the thread will sleep, and then the other thread can then, you know, feed the thing with data. This is basically, yes, it's producer, consumer, and fine wrapping. And then, you know, I know some of you guys are going to go, oh, context switches. Oh, context switches are so expensive. It means whenever you're doing a simple parser, you're reading everything in one function, you're doing it all immediately, it's fast. But with context switches, it's got to be slow. And we are doing research on this particular approach here. And one thing is that context switches, if you're reading from the network, like 100 kilobyte per second, so you get one context switch for every chunk, it's completely neglectable. If you're reading data that, you know, if you've got a lot of data coming at once, then you're going to do a whole bunch of stuff before you get a context switch. And then after you resume the context, then you'll continue parsing. But modern operating systems are able to switch contexts in a magnitude of from around 2,000 up to like 50,000 times a second. You will not see a huge performance impact from using an approach like this. It's pretty cool. You can look at the feed and the get car functions here for more details. This is an approach to writing an asynchronous parser in a thread. This here is, I'm just going to touch in on the topic of networking here. In Qt4, we support several event loops. So you can have a whole event loop running in a separate thread. And to some people, that is just a mind-boggling concept. But it's basically just that the code that you put in your main function, QApplication_app, return app.exec. In a thread, you already have an application, but there's an implicit event loop inside the thread. You can just call exec directly. And as long as your thread objects can live, as long as your objects can live completely inside the thread and communicate and work entirely inside the thread, then you basically just have like a complete separate event loop with a complete set of events being passed and concurrency. I think this is a very flexible approach to doing multi-threading. The example here shows that we create a QHTTP object, connect its done signal to the quit slot of the thread. The quit slot will exit the thread, will exit the event loop, sorry. And then, as you would usually do, you set the host and you get the path to some other file on a web server, and then you just call exec. And what happens here is that it enters an event loop. The thread will enter an event loop. QHTTP operates on an event loop. It'll do everything asynchronously. And once the whole operation is done, the quit slot will be called, the exec function will return, and then we emit the signal with all the results. So there's the pattern again. Emitting a signal with all the results. For SQL, I'm not going to go into SQL because I could hold a whole presentation about SQL, but this is basically the idea. You create one connection for each thread, and you do everything inside a thread. This first half of the code example shows that we're just creating a QSQL database object, and we're calling open on it to open the connection in that thread. And here we're executing some SQL command in that thread, extracting all of the data that we need using the record, and then emitting the results as a signal. This is just one approach to doing SQL in a thread. The good thing about this, I mean, the important thing to notice about this is something that we see quite oftenly, is that people confuse QSQL query, the object, for being a value type that you can just take out of a thread, pass it to somebody else, and have them extract data from your SQL record. And the problem is that it's not a value type. It's actively communicating with the database. You'll read more about this in the SQL documentation. So threads in Qt. Okay, so Qt uses threads. We're starting to use threads inside of Qt, and we're doing more and more of this. Earlier, our platforms didn't all support threads, so we couldn't really do this. But now we have potential to do. I mean, now we have the opportunity to use threads. QHostInfo in the networking module is a function that replaces the old QDNS class. It basically does a host lookup and returns you a list of IP addresses. And it can also do reverse lookups in 4.1. But the API we're using is a blocking API. The operating system doesn't provide a way to do lookups asynchronously like we would expect from an event-driven application. But we'll just call those blocking functions because it's done in a thread. So the thread will block, but the GUI will continue. And whenever the thread is done with this lookup, it'll emit the signal back to the GUI thread, which will then process, like open a connection on that IP address or whatever. And QHostInfo uses a lazy worker thread approach for this. And in QProcess, we're also using it for some technical problems, like, for example, handling anonymous pipes on Windows, or dealing with dead child process on Unix. If you thought that dead child processes was a problem on Linux or HPUX or whatever, then try to do it cross-platform. So in Qt, we've got some classes here. I'm just going to walk through this pretty quickly. You'll read more about this in the documentation, of course. QThread is the class that wraps the native thread implementation. This is one cross-platform interface into using threads on all these different peripheral platforms that we support and you may deploy on. It's very convenient. QThread storage is a class that provides a way for you to do thread local storage, which is storing data in a heap associated with a thread. There's also, of course, the QMutex. We've added QReader-Writer lock, QRead-Write lock for doing, reader-writer locks, basically. And QSemaphore and QWait condition. Just to take the QWait condition thing, wait conditions are basically that there is one variable that you can use for waiting on a condition. It means that a thread can go to sleep and be woken up when a particular problem has been solved. You use QWait condition typically in an environment where you need something to sleep, not necessarily in the context of I need to sleep until somebody else just frees up a lock, like you're using QMutex. QWait condition is also, I'd like to go to sleep right now and get woken up once the number of elements in my list is greater than 10. It's a very powerful concept. So this slide here just shows the difference between QThread run and the QThread object. QThread object itself lives inside the calling thread. When you create a QThread object, the QThread object will live in the calling thread. while the run function is what runs in the separate thread, in the new thread. Okay, so QThread has some signals. When a thread has started, it'll emit the started signal. When it's finished, it'll emit the finished signal. You can call start, which is a slot to start the thread. You can call quit to exit the event loop inside a thread if you're using the event loop. You can define priorities, and this is very important. Threads run with a different priority than your threads may run with a different priority than your main thread. In a cross-platform world, every single operating system might do different things. If you go real-time priority, time-critical priority on one process, Windows 98, nothing else will run. It won't schedule anything else. We can also adjust the stack sizes, as mentioned. You can adjust that you've got a 4 kilobyte stack size, and this is also very important. I'm going to show you afterwards that these metrics for stack sizes are very different on different platforms. We also provide a way of terminating a thread. Terminating a thread is evil, so we try to make this as hard for you as possible. There's a function called terminate. You can only call that if you have enabled thread termination through a static function in QThread. I'll get back to why a thread termination is evil. So we have signals and slots between threads in Qt4. You can connect a signal from one object to a slot in another object, and by default, the signal will be queued. The difference between a direct connection and a queued connection is that the direct connection is what you had in Qt3. It's just a function call. It's simply calling a function in direct context, which typically makes threaded programming funny. Odd things can happen if you try to call functions synchronously between threads, especially if you weren't expecting them to not be thread safe. You can explicitly set what type of a connection you want in the connect statement, as you're used to. The fifth argument specifying direct connection will override implicit queuing of signals between threads and do what you do in Qt3. If you know what you're doing, then you can use direct connection. Auto connection is the default, where it detects whether you're emitting signals between threads or within the same thread. So QObject, thread affinity. I'm storming through all these topics here now, but this is something that is very important. This is an essential part of the threading model in Qt4. QObject itself is not thread safe, but it is reentrant. And what that means is that you can use QObjects from different threads. I mean, you can use one QObject in one thread, another QObject in another thread. But this turns out to be a problem if somebody is passing events along. Because events are handled by an event loop, and the event loop is basically just a loop which calls functions on different objects, passing the event arguments as arguments. If we had one event loop in Q application that passed events to all these objects, that means that the whole event processing mechanism would have to be thread safe. That means that objects might receive threads while you're calling a function on that object. and that can lead to funny stuff. What we have done is that we've separated this concept now, so you associate a QObject to a thread when you create the object in that thread, not in the QThread, but in the thread, in the run function. So the QObject is conceptually owned by that thread. And then if you're passing events, sending events, then those are handled by the event loop inside the thread. And that basically means that you create a QObject. If you pass that pointer into some QThread object and expect it to be processed by another thread, that won't work out of the box. You'll get an assert. It'll crash. The proper approach is that you have to move the object to a different thread by calling QObject move to thread. You can read more about this in the thread documentation for Qt4. So back to the topic about cross-platform considerations. I'll do this a little bit quickly now. On FreeBSD, you can create something like 1,000, 1,500 threads or something like that. And each of these threads will consume 250 kilobytes of virtual memory space. So there's some of this stuff is actually reserved for use for the thread and unavailable to the other processes. On Linux, you can create 1,000 threads or something like that, but each thread gets 2 megabytes of virtual memory space. So if you're creating 1,000 threads, that's 2 gigabytes of virtual memory. Now try to run 2 of those applications, or try to run more. It won't work. HPX allows you to create 64 threads. And then, of course, the funny question comes, what happens if you don't have, if the operating system runs out of threads? Well, the operating system will nuke your application. There's no way of getting around that. And when you nuke an application, basically it crashes. Threaded applications crash spectacularly. Nothing crashes like a threaded application. Everyone knows that. That's why you, in general, try to avoid threads. If you've got 5 threads in an application, and then one trips over the soccer ball, then all of them will crash. In the meaning that they'll all halt immediately at the point where they were, leaving any file operations unfinished, meaning that there's can be garble everywhere. Maybe you've got a network connection where something didn't happen that weren't expecting it to happen, and suddenly it's very hard to find out what thread is actually the cause of the crash. There's usually one thread who's responsible, but it's not necessarily the guy that crashed. So you do a backtrace of an application, and it goes like, boom, it crashed at this place. Oh, you should have thought better than creating a queue-string. Typically, it's another thread that has messed up everything. So, but there's a way out. Basically, the debugging tools that we have available are very powerful. Threaded debugging is much harder, conceptually, than single-threaded debugging. If you create a 5-thread environment and it crashes, then your debugger will go, okay, it crashed. But then what you do? You typically need a way to switch between the threads and check the backtraces and see what context was each and every thread in at the point where it's crashing. So one of them is in the event loop. It's probably not his fault. Probably. So on Windows, Visual Studio is a wonderful tool. I must say that I'm envious, being a Linux guy, that debugging threads on Windows is very powerful. You can trace and step through operations across threads. You can switch from one thread to the other. You can suspend the thread and then resume it while all the other ones are sleeping. It's very powerful. Very easy to reproduce race conditions. There's also there's several other tools. It's very nice to use different tools when you're trying to debug a thread crash. If you're stuck with one tool, maybe you'll get the same condition over and over again. But if you try IBM Rational Purify for Windows, suddenly you'll get a completely different result. It'll go, hey, there's an out-of-bounds memory access at this point. And because of the complexity of a multi-threaded application state, Visual Studio might have missed it. And so it's useful to have many tools here. IBM Rational Purify doesn't allow the same real-time interaction with the thread, but it does provide a separate entity to give you a backtrace. And of course, MinGW has GDB on Windows. I have read on mailing lists on the web that it's suboptimal. The GDB implementation is not at its strongest in multi-threaded applications on Windows. But there are several other tools available. On Unix, we have a wonderful tool called Valgrind. Now, Valgrind is a tool for Linux, and I think there's also a couple of other platforms supported in the later editions. The cool thing about Valgrind is that not only does it give you a backtrace of the crash and tell you, for example, this memory was initialized there, might have been part of a block that was freed some time earlier, and by the way, that's the guy who made that block that was freed, and all these things. It also allows you to hook into other debuggers to get the interactive, the interactive part. And there's a cool feature that detects potential race conditions. Ooh, buzz alert. Potential race conditions basically means that you're accessing a segment in memory from 2 threads at the same time without using the native thread implementations of the platform, like pthreads. You're not using pthread lock before you're doing this. it's a fairly useful tool. Valgrind itself is very, very powerful. The race condition checking is something you should take with a grain of salt. GDB is very powerful on Linux and Unix in general. You can do like Visual Studio. You can break, you can step out between threads, resume, start threads and all this. And of course, it's a console application, so it doesn't provide the same feedback as Visual Studio does. But you've got DDD, which is a tool that can visualize it to some extent. Just want to mention one little thing. If you're stopping a threaded application and debugging and tracing through them, don't be confused about every time you do a timer. Q timers are just messed up if you step through a threaded application, because they'll fire at the same time. 1 second is not equal to 1 second when you're debugging a threaded application. Yeah, okay. So you've got IBM Rational Purify for Unix. You've got the Qt program, Ethnos Total View, which allows you to step between threads. And there are several other tools. I would suggest that you just see what the opportunity is, or see what is available for your platform. But the general message is that if you have a problem with threaded programs crashing and everything, try to isolate and overprotect all your shared data so that everything accessing data inside your thread is done synchronously, not threaded. Make sure that your application can run in single-threaded mode. Try to see if there's some way that you can serialize everything and see if, is the threading actually doing the cause of the bug? And third, and most importantly, try to stick to a threading model. Try to see if whatever you're trying to do is available in any of the models that you can find documented online or in the handouts here. So this summarizes my talk. Of course, threading is fun. We should all try to use threading more actively, not more than we should, of course, but don't be afraid to try out threading in your application, because you will get the concurrency and you'll get the feedback in your GUI, and threading is fun. So that was my talk. Thank you for your time.
Thank you very much to Andreas. We unfortunately don't have time for any questions, but Andreas will be available outside if you have any questions for him. Please fill out the evaluation forms and put them in the box by the door, and go to your next session or stay here. Thanks. Oh, and I also wanted to say that the presentations and the handouts from each session will be posted on the website after the conference in some days. I'm not sure exactly when, but we will do that.